Okay. Okay, great. Good morning, SVCW. Okay. I see the faculty member there. So reiterating the basic idea, right? So basic idea is remember last class, the last few slides I was just literally went through at bullet speed, right? Because some of those things I covered them in the past, and then all the mathematics part of it I took it away, and those are all extra slides that I put there. But I wanted to quickly reiterate what the basic idea of dynamic programming is. It's basically reiterating every single time we do, right? So that way you will get it finally. So whenever you want to, the solution that can be recursively described in terms of solutions to subproblems. Okay. So when we do that, then that is when dynamic programming is valid. Okay. Then we have this notion of optimal substructure. That was another buzzword that was used. Okay. Optimal substructure is nothing but it is alluding to the principle of optimality, right? Now we defined principle of optimality way in the beginning itself, right? Where we said that optimal solution to problem consists of optimal solution to subproblems. Okay. Now if you go back and recall the coin problem, right? We have this 13 cents problem where you can have subproblems to solve are 7 plus 6 or 11 plus 2. Okay. One of them is an optimal substructure and one of them is not. Okay. Students, I hope you remember all this, right? So between 7 and 6 and 11 and 2, which one we said was the optimal substructure? 11 and 2 we said was the optimal substructure because that will lead you to less number of coins. So whereas 7 and 6 leads you to a little bit more. That is the reason why we said the relationship doesn't flow either way. Okay, A implies B does not mean B implies A. That is what this one is saying. So if you choose the 7 and 6, the 7 solution is optimal by itself. The 6 solution is optimal by itself, but together the overall solution to solve 13 cent problem is not optimal. Because there is another solution called 11 and 2. If you choose those two, the overall solution is also optimal. Okay. So if you remember this particular scenario, you would be able to differentiate between optimal and suboptimal substructures. Okay. So that is one thing. And then you have some overlapping subproblems. Whenever you're doing a dynamic programming, when you break a problem down into subproblems, there's some overlap. Now, why, when you have that overlap, what we do is we solve these subproblems and store them in memory. We talked about that too. Okay? Because that way you don't have to recompute those problems over and over again. That is the beauty of dynamic programming. Okay? Now, here is the knapsack problem formally. Okay. So you are given some items. Items have weight, and then they have value. Whether you call it value or benefit, whatever term you use, it's still the same thing. There are three things, right? And then the goal here is to maximize the value. Okay. And then we are also given the fact that the maximum weight that knapsack can take. So we already know our objectives. The knapsack can hold only, let's say, X amount of weight. Okay. I want to put these items in such a way that I maximize the value. Okay. That is the knapsack problem. Okay. How do you formulate that problem? This is how you formulate it. Given a knapsack with maximum capacity W, and then you have a set consisting of n items. Each item has weight and a benefit or the value. Okay. And then you want to pack the knapsack to achieve the maximum total value. Mute yourself, please. Okay. So how do you put it in a formula? You can see that I am showing the formula here, right? So how do we read this formula? You want to maximize the benefit. The B is for benefit. Okay, and all these items belong to that set. Okay. With minus elements. This is the second condition. You want to maximize. If somebody is trying to talk.
So from Jntuk Moocs,
I'm getting some static.
hello sir.
1 second. Jntuk Moocs. Go ahead, tell me.
Yes sir.
Go ahead.
Sir, we are unable to see your
You're not. Okay, let me see. Let me do like this then. Let me share the. See again my window. Something is happening here. Hold on. Oh, the reason why you are unable to see is Jntuk took away my control back from you. Jntuk you can't see it because you have the control of the screen. Let me take the control back from you. Okay, I am now the presenter. Again, I am sharing my screen. Do you see it?
Yes sir.
You can put it in chat. Thank you. Okay, so I just showed one slide before that. I hope you saw that, right? So this is the formal knapsack problem. Before that I showed you that slide, right? So basic idea I reiterated. I said this is the formal knapsack problem. Given some items, pack the knapsack to get the maximum total value. Okay? Now, so to formulate that problem, ultimately when you do that, we want to maximize the benefit and not exceeding the weight of the knapsack, right? So mathematically, how do you show that? You see the last bullet point here. Maximize the items in that knapsack where the benefit value, B stands for benefit, okay, is what you want to get, maximum benefit, subject to the fact that for all the maximize, for all of that, sum of the weights of all the items should be less than or equal to W, okay. So weight of the knapsack is the limiting, and we want to maximize the benefit. Okay. Okay, perfect. You can see my chat. I'm trying to arrange my windows here. Okay. Now, if you do the brute force search, which we talked about, if there are n items, the combinations of items are 2 raised to n. Basic computer science concept. We know that, right? Okay. When you do that, obviously the running time would be order of 2 raised to n. That is no good. Okay. Now when we do dynamic programming, we have to, the trick is to find out the sub problems. Okay. Pay very close attention. Okay. It gets very interesting from here on. Okay. So we need to somehow identify the sub problems. Okay. The whole idea is how do we identify that? That's what distinguishes the super guy from an average Joe, right? Okay. Now let us assume as a first pass that we do like this. Okay. Like all the items are labeled 1 to n. Okay. I can have a sub problem for some k, right? K is less than n, right? Then it becomes a sub problem, right? I have 10 items. I want to solve the sub problem with 5 items first. So I'll choose 1 to 5. Okay? Legitimate. Okay? Now what happens when I do that? Hard to see. Let me expand it hopefully. Expand it hopefully. Slide more in. Okay. So here, when you see that the item is the weight and the benefit, the benefit That's why you see S4. He chose a subproblem of 4 elements out of those 5. Okay. Now, if you carefully see which 4 he chose, this Wi equal to 2 and Bi equal to 3 corresponds to item 1. W2 equal to 4, B2 equal to 5 corresponds to item 3. Right? And Wi equal to 5, B3 equal to 8 corresponds to item 4. And then you have 3 and 4. That is 2. So he chose 1, 2, 3, 4. Now when you do that, you have the total weight, maximum weight you have defined is 20. You already defined that. So for that subproblem, you get the total weight equal to 14 by adding the weights. Simple arithmetic, right? And the maximum benefit, you sum of the benefits, you get 20. Got it? Okay. Is there anyone who does not understand S4? Don't understand, ask your faculty member to put it in chat and I'll explain it one more time. Chose corresponding to item 3, okay? 5 and 8 is corresponding to item 4, and 9 and 10 corresponding to item 5. So he skipped 2. Originally he took 1, 2, 3, 4. The second one he took 1, 3, 4, 5. Right? So when he did that, he is getting the total weight is 20. That is the limit, and then the maximum benefit is 26. Okay. Now here is the problem with this, right? Obviously, second solution is better than the other one, but then when you're breaking it down to sub-problems like this, it goes back to the same thing. Whenever you're in doubt, go back to the 13-cent coin problem. That's a great cheat sheet, right? Whenever I'm learning something, I always have one analogy where I can always go back to. When I forget something, I go back to that, then I will know how to do the problem, right? So, the idea of solving it is such that when you do in 0-1 dynamic programming, you should be able to do recursively, right? So the solution for a higher problem should be composed of the solution to the factorial or Fibonacci sequence, right? So when you do factorial 5, factorial 4 is a solution to factorial 5. So you need to have that condition there. In this case, that is not true, because the solution for S4 is not part of solution for S5. You cannot come up with S5 solution from S4. Okay? That is one problem with this. Okay? So how do we fix that? Believe me, these are a beautiful set of slides. I didn't create all of them, okay? I merge a lot of slides from all the things that I've done for so many years, right? Okay, so the way that he fixes that problem is he just adds one parameter. See the third bullet here? Okay, remember this is dynamic programming. You have to be creative. You have to be creative. You have to be a creative programmer / algorithmic designer. I said let's add the weight. Okay, now when he adds weight for each subset of items, this looks like this. Okay. What we are going to compute is the benefit of k, comma, w. Now all of a sudden, this benefit, the subset of items is also added there. Okay. Now when you do that, okay, by adding that, now it gets to be a little bit mathematical here, but you can go back and convince yourself. All he's doing is he is now able to come up with a recursive formula for the subproblem, right? He has to define the base condition here, k minus 1 to w. Remember we said a to k is less than or equal to n if the series of n items, and then the weight cannot go beyond the actual weight limit of the knapsack. The goal here is to maximize. How do you maximize the benefit of k minus 1 with the w factor? K minus 1 w minus wk, because if you're taking one element here, you already have certain weight. The balance weight is w minus minus Wk. Okay? And then you continue to add the benefit value. Okay? So he formulated that equation to maximize the benefit, at the same time taking into account the weights. Okay? Now, oh sorry. Okay. We'll go through that a couple of times. Okay? Now, so equation means is the best subset of Sk minus 1 that has a total weight W. What we are seeing this equation means is the, okay, mute yourself please. Mute yourself please. Thank you. So what we are basically saying is, hey, what is the best subset? Hey, what is the one which has a total weight W, or the best subset that has total weight plus the item K. So there are basically two paths here. Okay. Now when you have those two paths there, okay, what happens in the first case? When the weight of K is greater than W, it cannot be part of the solution, right? We know that, right? So we have a formula, but this is plain English terms. What does it all mean? Okay. So when you have the Wk which is greater than W, that doesn't work because the weight has already exceeded. So that's unacceptable. And in the second case, Wk is less than or equal to W. Okay. Okay. And then which item goes there into that? All we are saying is the item with the greatest benefit goes into that. That's all we are saying there. Okay. Now how does it look? The algorithm itself. Again, I don't expect you to understand 100% of it, but you get the idea that, hey, it all depends on how you formulate the sub-problem. That is number one, right? Then the rest of it would become easy. It becomes much easier when you write code also, by the way. You'll understand it better, right? So by formulating that like that, here is an algorithm which says for all the weights 0 to W, okay, so he's initializing some array. Okay, I'll show you how this entire thing visually flows. Okay, that's what these slides are. Okay, now he's going for all the items. Okay, he's initializing the first for loop here, right? He's initializing bi 0 to 0. Okay, that means this is the full row is becoming 0, right? Okay, so he has initialized the array. Then for every item and recursively for every weight 0 to W, you are going to first make sure the weight Wi is less than or equal to W, because you know that if as long as it is less than W is what the knapsack weight, right? So as long as it is less than the knapsack weight, we know that it can be part of the solution, right? You understand that? Okay. Now, once we know it's part of the solution, then he's going to compute the benefit value. So you want to, this basically if then else shows, you want to basically compute the maximize the benefit value. Okay. Okay. If that particular one is going to exceed your weight, then you get to the last else statement here. Okay. Now notice one thing. How do we compute? Now, can you come up with this algorithm? Can I come up with this algorithm like this? Yes or no? Depends, right? Depending on how you write and how I write, we could come up with different algorithms, right? There are so many variations of 0-1 knapsack problem in dynamic programming. People continue to do research on that still. Okay, but this is one example. Now, how does he compute the running time? You can see here how he has given, right? For W equal to 0 to W, BOW equal to 0. What is the order of that? W. By now you know that, right? Because you have to do it for all the items. Okay. Same thing for I equal to 1 to N. You are initializing it, but you are repeating it N times, right? So if you look at the code here, since you are repeating it N times, you basically get the order of W there. This second part, this for loop is N times. Order of W is same order of W again, right, in the big O notation. But since you're repeating it N times, you get N star W. And what was the brute force algorithm that we talked about for N items? 2 raised to N, right? That was what we said. From 2 raised to n, using dynamic programming technique, where we solve the subproblems recursively. I mean, granted, you need to figure out what the perfect subproblem is. Okay, that's not easy, right? But once you know how to do that recursively, you are able to reduce the running time significantly here, right? Obviously, for larger value of n, you will begin to see big differences. Okay, let me pause here for a second. Anyone has questions? Okay. Maybe if you have your question, you can hold on to it, because we'll run that algorithm on an example, so that way you will better understand it, right? First the theory part, now the actual demonstration part, right? So let's assume we have 4 items, and the maximum weight that we want in the knapsack is 5. And the table is shown as a tuple right here. So you have 2, 3, 3, 4, 4, 5, 5, 6. The first numbers are the elements, items, and then the second numbers are the benefit, right? Value, weight, and then the benefit. 4 items. Okay. So how does the algorithm work for these 4 items? This is very nice, huh? I don't know about you. When I was putting together these slides for you, I felt very happy. I can tell you that. Okay? Good set of slides by the author. So the first for loop, 0 to w, b0w, you initialize all zeros left side. Now you did the first for loop for I 1 to n, you did bi 0 equal to 0. So you get a 0 by 0 there. Okay? Okay. Now you apply the rest of the logic there. See, if wi is less than or equal to w, that means item I can be part of the solution. Okay. So when you're talking about part of the solution, by following the rest of the steps, you can see that you have filled the table cell 2, 2, where you get the 0 there. Okay. Now if you go to the next trace here, okay, then by going through that for loop, students, I mean, you are already capable of programming, right? If you follow that logic that I'm showing on the screen there, you will see that the item that gets filled is the value 3. Okay. I1, 3, you can see the benefit on the right side too. For convenience, I gave you that one. Okay. You literally take a sheet of paper and follow these things, write them down on a sheet of paper. Then you can convince yourself these values that I'm showing you there are correct. Okay. If I were you, I would do that. Take a sheet of paper. When I give you exercise time, you can trace this. Okay. Now you basically apply that, trace everything. The rest of the slides here basically show, as the algorithm is executed for that 4 items, how the sample values are changing in the table. So at the end of it, what do you expect to see? You expect to see the full 2 by 2 table to be filled up. Let me check if they are filled up or not. I don't know. Okay. So you can see each provided every snapshot. Okay. Provided every snapshot. Okay? At every stage of the loop. Okay. Final. There's one more, I think, after this. There you go. So by doing those things, you can basically fill out the table, and then somewhere I didn't get the highlight here. You would notice that basically by using items, is it 2 and 3 or is it 3 and 4? Which one is giving you the maximum benefit here? 3 and 4, right? Because they add up to 7. Maximum value, and then 1 and 2, my mistake, 1 and 2. If you look at it here, if you look at the row 1 and row 2 here, you can see the values, the weight, they don't exceed weight, it's exactly equivalent to 5 as stated by the problem, whereas the benefit would be 7. Okay, so that is what this set of slides basically showed is, hey, we we recursively apply that algorithm. First come up with the table. Okay. Mute yourself, please. Somebody asked a question. Okay. Somebody, let me mute you first, then I'll answer the question. Give me 1 second. Oh, thank you. You muted yourself. Thank you. Okay. The question that was asked is, we can obtain optimal solution for a knapsack problem using 3D method. Then why do you choose dynamic programming? Okay. Now, who said that that 3D method works for knapsack problem? You are going to do an exercise for that. Okay. Hold on to your thought for 1 second. I'm going to show you something quickly here. Sorry. Good question. Hold on to your thought for a second, okay? We'll have fun with that. Now, if you notice, for this particular algorithm, what we found was the maximum possible value that can be carried in a knapsack. That means we know the value. I know the benefit is 7, okay? But which items to put in the knapsack, this particular algorithm did not compute. Okay? So we need to I'll answer that question to Jntuk Kakinada. Hold on to your thought. Okay? So, how do we know the items that need to be put? You have to extend the algorithm. Okay? And I show you how to extend the algorithm by giving you an additional piece of code here. Okay? And then I trace all of them, apply that algorithm. Okay? You trace those things like how we did for the previous half of the problem. At the end of this exercise, you would get which items to put to. Okay? So there's some highlights I put there. Ultimately, you'll figure out that it will be 1 and 2 items. That is how you will come to the thing. Okay? This requires, believe me, students, if you want to go deep, it really requires for you to trace it. I strongly recommend that you trace this, okay? Don't take it lightly. I gave you the full trace of it, okay? Now, what is the summary of that? The summary is, it's a great technique. We clearly saw the big O notation, right? W times W star n versus O raised to 2 raised to n. Big difference between the two, right? But the trick is you should know how to define it recursively in terms of these partial solutions. You could do that and you can store that and reuse them. Several classes ago I told you about this terminology called memoization. That basically means you're storing it in a lookup table. I even use the word lookup table. Okay? Now, to answer your question that was posted here, we have a small, I'm making a claim, okay, that yes, whatever Jntuk Kakana answered, I agree with you. Fractional knapsack greedy works, but for 0-1 knapsack greedy does not work. Okay, Jntuk to everyone, right? Got it? Okay. So it cannot be solved. Now, how about we prove that? This is where I want you to do the following exercise. Time for your exercise, right? Okay. This exercise is a simple exercise, okay? But time for you students to do this exercise where we are saying the knapsack problem cannot be solved with greedy method. And your goal is to prove it. And the way you prove it is the following, okay? You are taking 3 items weighing 10, 20 and 30 kilos. And the knapsack weight is 50 kilos. Okay? And I'm already giving you the value of the second item. 20 kilos. One is rupees 100. Okay? Now what I want you to do is assign the values to the other items so that the greedy algorithm fails. Okay. So this should answer the question first posed by Jntuk here, but they themselves answered saying greedy works in fractional knapsack, but it does not work in 0-1 knapsack. Now, recall student, what is fractional knapsack? Fractional knapsack means you can take part of the item. Obviously, it's a metallic thing that you cannot break. If it's something like powders, let's say, these items are sacks of chemicals, okay, where you can take less powder, then that works. That is called fractional knapsack. In 0-1, it's all or nothing. You either take the item and put it in the knapsack, or you take it in the knapsack, or you don't check, or you don't take. Now, small exercise just to stretch between the lecture. Take 5 minutes. Now the time for you is 11:32. 11:37 we'll. I'm back. You can answer Suchaya already? Anyone put? So somebody gave, Jntuk gave some answers. Okay. The idea here is I want you to disprove it, okay? You can get optimum. What are the values that will break it? That's what I'm asking you. So you have to come up with some other values which would break this solution, okay? Okay, great. So you can post it in the community also, whatever those values are, okay? I'll move on because we want to get to the backtracking after giving you some insight on traveling salesman problem. You can put it in the chat and we can come back to the answers even at the end of the class. Okay. Traveling salesman's problem. Let me give a little bit of, we kind of covered flavors. Even the very first day I said go do the Dijkstra's shortest path problem. So those are all like all those classes of problems, like each approach problem for you. Remember in this a few weeks ago we gave a tree. That I've been introducing this in bits and pieces for you, but here I just bring it all together to tell you what this is, okay? Okay, so how can we prove that greedy doesn't work for 0 and y? Okay, I'm going to give you the couple of values, okay? Hold on to that. Hopefully, I never really saw what those values are. I just have to come up. But at the end of the class, I'll put the values there, okay? To show that it doesn't work. For information, we did other problems related to that where greedy is not an optimal solution. Remember the coin problem that we did? If you apply the greedy approach, the coin problem, depending on the denomination that you have, it won't work. It won't give you the optimal solution because greedy always takes the highest value. Right? That is the purpose. That is the whole idea around that. So while I'm doing this one, you can, if you want, you can go look at that coin problem where I show it doesn't work. It's the same concept here. I'll show you how it doesn't work. Okay. Let's go to Tsp here. Here is the formulation of the problem. Given a list of cities and the distances between each pair of cities. Okay. What is the shortest possible route that visits each city exactly once and returns to the origin city? Okay, you are making a loop. Okay, that is what this is. This should trigger some things in you. Remember we did the all pairs shortest possible algorithm where I showed you the distance between each of the cities and things like that. All of those things help in solving the Tsp problem. Okay, let me see what that is. I should actually take back my word, right? I shouldn't say it helps in solving, okay? You cannot solve a Tsp problem. It is called an NP-hard problem. If you take automata theory I don't know if JNTU offers that class or not. We talk about a class of problems in automata theory, those that can be solved in polynomial time, those that can be solved in non-polynomial time, and those that cannot be solved even in non-polynomial time. Those are called NPR problems. Okay? This class is not meant to talk about that in gory detail, but basically for general layman's term, the ideal solution for TSP is non-solvable, the way it is formulated. Now, does it mean that we keep quiet? We don't. Right? Okay, so that's, one author said that it's easy to state but difficult to solve. Okay? Now, in your syllabus, this concept of Hamiltonian circle or a path comes in the next chapter, but I did put a slide. I put a slide here as well because it is discussed in the context of TSP also. This was something that was formulated almost 50 years ago. Okay? The definition is a route returning to the beginning is known as a Hamiltonian circuit. You visit each and every node and come back. Only the source and destination nodes are one and the same, and they are visited twice. Every other node is visited only once. So if you have a network where you visit every node exactly once and come back to the start, starting point, then it is the Hamiltonian circuit. Now, if you don't need to, then as long as you count the graph, you get the Hamiltonian path. Again, all of these things fall under the same umbrella of TSP. Where do we have TSP? Apply sales problem. Not having sales problem, right? Seeing there, it's definitely something is not quite right with the WebEx. My apologies there. I will let Cisco know that my students had a terrible experience using WebEx today. How about that? Okay, great. So there are so many techniques, right? We know that. And we know what the traveling sales problem is, right? So now, what are some of the heuristic approaches, right? So a list like, for example, somebody used optimized Markov chain algorithms. Don't even ask me what Markov chains are. 25 years ago, I learned that in numerical analysis and methods class. I don't know if you learned that in JNTU now or not. That was the first and last time I learned about that and forgot all about numerical analysis. Okay. Now there is a algorithm, heuristic means it's seat of the pants, right? So you just come up with some idea, do it and hack it. So you have a local search, meaning you start with a valid tool, then use some local moves to improve the tool. Okay. Now, nearest neighbor. This kind of almost like find the nearest unvisited node. Almost like greedy, right? Whatever is the shortest path. It's almost like taking the shortest path, right? That is one nearest neighbor thing, and greedy algorithm, of course, right? Always start with a empty partial tour, add the smallest edge. We did that. When we did the shortest path Dijkstra also, we said we can use the greedy algorithm to solve the Dijkstra's problem, right? You can see the computation times for that. So there is some ways of doing that. Exact solutions too. I do not know what the cutting plane algorithm is, because I don't really program much in linear programming. But if somebody is interested in that, what I would recommend is they should research that, whether it's a faculty member or student. You can present it to our class on the last day, what that would be. That seems like an interesting technique here. Okay, you can see that when they applied that algorithm to Germany, okay, they came up with the answers for that. Okay, for 15,112 German cities. They calculated that. Same thing was done in China also, I believe. Okay? But we do have a class of algorithms called branch and bound algorithms. Okay? So we will revisit this TSP problem when we do that in the next unit, where we apply some branch and bound techniques to solve this. So leave it like that. Something else which we learned, which is very useful in solving the TSP problem. Okay. So remember, students, you all learned about trees, right? And then I spent some significant time talking to you about minimum spanning trees. Okay. This is a classic way of solving a TSP problem. If you look at the cities, like if you look at the traveling salesman, if you model it, it is nothing but a graph, right? Going from city A to B, C, D, E, F, G, H with some weights and then coming back. Okay. Now, we discussions on trees. There's something called minimum spanning tree, right? What is the spanning tree? Before we talk about minimum spanning tree, we learned about spanning tree, right? So spanning tree is basically a tree which contains all the nodes, no cycle, right? That's what a spanning tree is. Root to the leaves, all nodes covered. That's a spanning tree. Okay. Now, if all of those edges have weights, whether they are costs or distances, whichever tree, so a spanning tree, there can be many spanning trees. Okay. Whichever spanning tree has the lowest weight is the minimum spanning tree, in essence. Okay. So what we do is we model the TSP problem as a graph with non-negative edges because they have to be positive, and we want to find a cycle that visits all vertices at a minimum cost. That's all we are doing. So we took the TSP problem, transposed it into a graph, and then we do the analysis. Okay? So how do we do that? So if you have a cost, C is for cost here, and then you have two edges in a graph, and then you have CUV denote the weight of the edge. Okay? So we are taking this English text here, formulating it as a mathematical problem here. Okay? So given a set of edges, okay, some set of edges A, we form a tour. The tour is C of A. C of A is nothing but the sum of edges weights in that tour. All the edges that belong to the tour that we are interested in. Tour is nothing but visiting the cities. Now, to do this one small concept is there, which you should know. Pretty silly concept, but it is important too. We use something called triangular inequality. Whenever we talk about these trees and minimum spanning trees and all that, right? I would almost call it an axiom. If there are pure mathematicians in this audience of faculty members, they would kill me for saying that. It's like basically what we say is, when you go from U to W, the cost of going directly from U to W is always less than or equal to the cost of going indirectly. Meaning between U and W you have a V. It's kind of like what do you say, you want to go from Hyderabad to Kakinada, there's a cost. Okay. If you want to take a detour from Hyderabad to Kakinada via Vijayanagaram, right, that cost would be greater than going from Hyderabad to Kakinada. Okay, or at most equal. Okay, so we apply that principle when we try to solve this problem. Okay. Now how do we do that? Okay. Here is the thing. What is the relationship between TSP and MST? TSP is the traveling salesperson problem. MST is the minimum spanning tree. See the thing that I highlighted in blue here. Okay. A TSP is a loop, right? Because you're coming back to the same source. Source and destination are the same. But if you remove that one edge, then it becomes a tree, because trees do not contain cycles. Okay. Now once you understand this, once you know this insight, then the second bullet makes sense to you. Okay, because now the cost of minimum TSP tool is at least as large as the cost of the minimum spanning tree, right? Once you make it into a tree, you know there exists a minimum spanning tree which gives you the minimum cost, correct? So the TSP tool is at least that much, and the reason why it could be more is by completing that last edge, because you still have to travel that last edge, right? Coming back to the source. So it could be in that range. Okay, so far so good. Now, how many of you remember the fact that we talked about Kruskal's algorithm and Prim's algorithm to arrive at minimum spanning tree? Let me see any videos here. Do I see any videos of anyone? Okay, I see Chaitanya videos. Do you remember the terms Kruskal and Prim? Show of hands. We learned that. ఎప్పుడో నేర్చుకున్నట్టుంది లాస్ట్ ఇయర్ కదా. Right? Okay, I'm seeing Jntuk Kakinada. Do you remember? I think Jntuk Kakinada guys actually gave some good explanations of Kruskal and Prim. Show of hands. Do you remember that? Yes, I see some people raising hands. So basically we use those algorithms to arrive at a minimum spanning tree. Now I'm not going to teach you again what those algorithms are. If I remember right, I actually put the algorithms in the slide deck too for you. Okay, so what did we do? We basically took, to recap, is we took the traveling salesman problem, converted that into a graph, removed that last edge, right? Because you don't want a cycle. Then it becomes a tree. Okay, you avoid the formation of that cycle. Now once you have that, then you know how to do spanning trees. Since we know minimum spanning trees, we know minimum spanning tree gives you the minimum cost. Okay, and we can apply any of these algorithms, Kruskal's or Prim's, to arrive at the minimum spanning tree. So whatever value you come up with, you just add the value of the last edge that you removed. That's your best cost. Okay, very, very neat, huh? Very creative. I mean, that's why I love computer science. It's always about solving problems like this, right? Okay, what am I doing here? There's another algorithm. This is from a research paper that I put. I don't know if this is part of your syllabus or not, but it's interesting to know, right? And I'll actually upload that paper also into the community. So what this guy does, very interesting algorithm he came up with. I just discovered it recently. So when you are given a problem, he comes up with what is known as minimum spanning tree. Easy way. Take some small problem, right? But look at the beauty of this algorithm. See the second picture here, twice around tour. So what he does is, it's called a twice around tour, meaning every node is visited twice. Okay, twice around tour. So he has a double linkages. If you follow the graph here, you can see that 2 times you are visiting the node. Okay. Now once you have a twice around node, from there, because of the intelligence shared between the nodes, so to speak, you will start discovering shortcuts. Remember, we have the concept of shortcuts, right, in real life. In Hyderabad, whenever I go from A to B, I always go through, in Hyderabad we call them gullies, right? Gullies means what? Streets. So I always have shortcuts. So you discover what those shortcuts are, you share that knowledge, and then you start removing the non-shortcut nodes. Okay? Beautiful concept in this picture. Huh? Now once you get these non-shortcut nodes, you basically come up with an optimum tool by start going through that. Because all you have is, all the edges are nothing but shortcuts, right? So, and then you fill out the last edge. See how we formed a cycle? We formed a cycle going from start follow the arrows, you come up with that. Okay, so that is the closest approximation to solving the total salesperson problem. Okay, he gives the algorithm here. You can see here you have the T, which is minimum spanning tree. Take any vertex, list all the vertices visited by a pre-order walk. How you visit them? Remember we talked about pre-order, in-order, post-order traversal of the tree. That's what you apply here. You apply the pre-order walk, starting with R. Okay, ultimately you return the length. Okay. That is the algorithm for that. Questions, comments? That is basically, I do not know what kind of final exam questions you do get. When I give exam in this, what I typically do is I give some pictures like this and ask them to compute the, come up with a spanning tree, because I know that's the algorithm that students are comfortable with, right? And then I say, okay, can you come up with a minimum spanning tree? And based on that, estimate the total cost of the tool. Okay, and typically I give about 4 to 6 nodes, not more than that. Okay, that is that. Jntuk Moocs, I have not forgotten about your thing about disproving the knapsack, right? Greedy does not work in knapsack. I'll disprove that. I have not forgotten. I wanted to jump into the next set of slides where we get into backtracking. I should probably backtrack from the last slide to the first year. I should apply that and see how it works, right? Okay. Faculty members, you want to add anything? By all means, you can add. At the end, I'll give you 5-10 minutes if you want to add your wisdom. As always, you're welcome to do that. Okay. We are in Unit 5. In case you want to know where we are, let me share my screen here. Share. Application, Microsoft Word. Okay, I'm sharing Microsoft Word document. We are in Unit 5, backtracking. So I'm going to talk about general method. I'm going to talk about n-Queen's problem. I'm going to talk about graph coloring. I have something about coloring today. I have not put the slides yet about sum of subsets problem. I'll probably introduce you to it if we have time. And then we'll finish the rest of it in the next class. By Monday, we should be done with Unit 5. Unit 5 is pretty straightforward. Okay. SVCW faculty member. So please be assured we have enough time to cover Unit 6. Not only that, I'll do an extra class as I told you. And then I'll also do a revision for a final exam prep class for students if they are interested. Okay. Having said that, let's jump into backtracking. I already posted these slides here. Students, I would like you to review all these slides before you come to the class next Monday. What is backtracking? Let me spend some time. Okay. Chat. I could bring the chat. 1 second. Okay. So, what is backtracking, right? Kind of like backtracking is not like taking back your word or something like that. What we do is, right, here is the scenario. You want to make decisions, okay? Life is all about decisions, okay? Every day you get up, you have decisions, you have choices, okay? But most of the time we make these choices based on imperfect information. It's either imperfect or incomplete, both in general, okay? Here, more like we don't have enough information, okay? Now, whenever you make a decision, you get different choices, okay? That's pretty intuitive, right? All of you understand that, okay? I mean, I can give you a lot of nice humorous examples between boyfriends and girlfriends on that, but in the interest of time, I won't today, okay? Now, what happens is when you make some sequence of choices, you can either reach a dead end or you could find a solution to your problem. Okay? So you have choices, you have decisions, and then you have to take back your decision sometimes, change your direction. It's kind of like backtracking, realistic example. I can give you a realistic example of my own nephew. It's a little bit embarrassing to give that example. Give it anyway, right? So I promised my late dad before he died, don't worry, I'll take care of him and I'll join him in engineering, because my dad was a great professor and he wanted his grandson to become an engineer too. I knew in my heart that that guy is totally useless. He just doesn't have engineering capability, right? But we joined him anyway. Now it's now 6 years and I do not know how many lakhs of rupees in private engineering colleges I spent. Now he's backtracking. He made a decision to do that. He's failing, and the last I know he still has 35 courses to pass. That's as good as doing 4 years worth of college. Now he's trying to backtrack and do something else. Okay, that is real life backtracking. Okay. Now, what is this technique, right? So when you have a large search space, okay, you're systematically trying and eliminating possibilities. Note the word systematically. You're not doing it randomly. There's a system to it, okay? Now, everyone knows mazes, right? I do not know in Kakinada and all, here every Halloween time we have corn mazes. You know what a maze is, right? You have to go from one end, come out the other end. And they're always, depending on which path you take in a maze, you get stuck. When you get stuck, what do? You backtrack. You go back to your previous known point, and from there you try another entry or a distance or a path, right? So that is the maze. Okay. So whenever you are in a maze, you have two options, right? Which direction to go? You could have two, it could have three, who knows, right? But that is the concept of a maze. Okay. So he's explaining here, right? Go through portion A of the maze because he defined A, B, and C, different categories, right? If you get stuck before you find your way out, then you backtrack to the junction, wherever you came, where that decision was made. Should I follow A? Should I follow B? So when you backtrack, you already know that the portion A will not lead you out. Now, since you're a computer scientist, you say, that is useful information, I need to save it somewhere. Okay, that's what you should be thinking as a computer scientist. Now you will go to portion B. Okay. So basically at every junction, you will have a choice to make. It could be 2, it could be 3, or whatever, right? What the backtrack strategy says is, try each choice one after the other. If you ever get stuck, backtrack to the junction and try the next choice. If you try all choices and never found a way out, then there is no solution to the maze. Most of our data structures and analysis students here, we write a program for solving the maze problem. And just to give you some idea. So this shows pictorially how it works. It's not put in animation, but it shows like you start here, you go, you get dead end, you backtrack, you see the back arrows coming from the dead end, and you go here, you have a decision point to make. Question marks are junctions where you have decisions to make. Okay? Dead end, ultimately there is one success path. Okay. Give me a second. Now, quick terminology on trees again. The reason is tree comes everywhere. Remember, I spent so much time on trees. There's a reason why I did that. Right? You can see how all these things are coming in handy for you now. You have the terminology, you know this, right? Parent and children, okay? We typically draw parent root at the top. Even though we call it a tree, we draw the root at the top, unlike the natural system where the root is at the bottom. But there is some trees where the roots are on the top, right? Like the banyan tree or something. Okay. We typically use some data structure, okay? And then to show diagram of the sequence of choices, and that's the reason why it looks like a tree. Okay, so the algorithm basically sweeps out a tree in problem space. That is what we are doing. Now what does it mean? Okay, here is a simple algorithm. Okay, very easy algorithm, by the way, much easier than dynamic programming. Okay, so we explore each node as follows. What do we do at every node? Okay, if that is your goal, you already reached the node, so you say success. But if it's a leaf node, then you return failure. Okay, now if it is an intermediate node, then it has children, so you explore each of the children. If any of the children are successful, you return success. You are in the loop. And so you considered the root node, you considered leaf node, intermediate nodes, right? Let me check here. Okay, that's the algorithm for backtracking. Okay. Questions? Okay, how do we apply that? What is the classic problem? I was asking Chakravarti garu today, hey, do you have a chessboard in your class? I can have the students work on it, right? Let me see, do I see any videos here? 1 second, my system is stuck here again, I think. I see Chaitanya, girls. Do you play chess? Are there any girls who play chess there? Can you raise your hand if you play chess? 1, 2. So how good are you? Are you like that Koneru Hampi? Okay, I love to play Koneru Hampi and see if she can beat me, right? Okay, 8 queens. What is the 8 queens problem? Fantastic problem, right? Every computer science student should write an algorithm and a program for solving 8 queens problem. So what is the problem? Problem is you have to arrange 8 queens on the board, 8 by 8 board, such that no 2 queens are attacking one another. Okay? And for those of you who play chess, you know that queens can move down any row, diagonal, or any column, right? So long as there are no pieces in the way. Okay? The only thing queen cannot do is jump like a knight. That's why we love knights, right? Knight is the only thing on the board where you can jump. Okay, so because of these things, you know that you can only have, due to these conditions, right? Each row and column of the board should have exactly 1 queen. How do you arrange that? Okay, that is the 8 queens problem. Okay, now here is the algorithm for that, right? Place a queen on the first available square in row 1, which is row 1 here, I think on the top one, I think. Okay? You're solving it row wise here. That's based on the algorithm, right? I don't know whether I can call it row wise, I can also call it column wise. So faculty members can help me with that. So then you move to the next row. You place a queen on the first available square there. Okay, and how do you determine the first available square? There is no conflict with the previously placed queens. Okay, you can see if you go from the top, first you come second row, you come here, you put the queen here. Okay, third row, so it's almost like 1, 3, 5, right? You'll be tempted to say why not 7 next, but we always look for the first available thing by the time you come to row 4. Okay, continue like this until you have solved the problem or you get stuck. Okay, so when you get stuck, remove the queens that got you there until you get to a row where there is another valid square to try. This is very important, huh? When you get stuck, remove the queens that got you there until you get to a row where there is another valid square to try. That means you are shuffling the deck here, right? You place something here, but whenever you're stuck, you go back, meaning you're back. Remember, when you get stuck in a maze, you go back to the previous step. The previous step is where you put the queen. right? Then you move that queen to some other square. So that way the next queen can be put on the square. Okay. In general, do you understand the problem? Okay. Now, it is nothing but you visualize that as a tree, okay, that I've been trying. That's what you do. Okay, everything is a tree here. Okay, I'm not using a board to show you the thing on the board, but I showed you the diagram, right? Okay. Now, the wonderful thing about that, it's a recursive algorithm, right? So I'll show you the code also in a second. Okay. Here is the code there, piece of code. Okay, you have different arrays here, where it shows like it gives you explanation, right? Stores a valid permutation of queens from index 0 to location -1. You keep track of the locations where you place the queen, right? And you keep track of all the things, rows in which, so you have to track your path, right? Okay, and you can see here how this is solved through an algorithm here. I'm not going to go through each and every row here, but you have comments here, right? So if you found a solution, you're printing it right first there, right? If location equal to size. Okay. Otherwise, you go through that integer I less than 0, I plus plus, right? So you're looping through all the possible rows to place the queen. Okay. And then you are going to try this row if it hasn't been used, right? You have to first check whether that row has already been used. If it is used, you cannot use it. Okay. Next, you check if there is any conflict. Okay, because you have to keep track of rows, columns, and diagonals. Okay. You look if there is any conflict. Okay. If not, okay, because it says if not conflict, right? If there is no conflict, you mark the queen in this row, and then do all these steps that shows there, the 4 steps. Okay, pretty straightforward algorithm. Okay. Now, if you do that, there's some analysis here. You can see if you do a brute force algorithm to do the permutations of the numbers of 1 through 8, you can see there are 40,320 combinations. Okay. Now, if you do a backtracking algorithm, it's slightly better. Okay, it is not only slightly better, I would call it significantly better, because your possible queen placements, it comes down to 15,720. From 40,320, you have brought it down to 15,720 issues. Okay, now you can see there is a further improvement here, where you can do it in 5,500 steps. Okay. That's another type of algorithm there. There's so many algorithms, right, for queens, 8 queens problem. So you can see here simple backtracking that I showed you, 15,720. If you optimize it further, you get 5,508. Okay. Now, one of the things that you see when you implement it, you can see most of the things that we do are depth first here. Okay, by doing a depth first search and then pruning off on the rows and columns which are not valid, you are able to optimize that. That is what this says. So that is the 8 queens problem. Let me stop here. I saw a couple of classrooms vacate. Do they have other class, or did I exceed the time here? I was not sure. I didn't stop there to check. I think we still have 10 minutes, right, or 6 minutes. Okay, let me stop here because we only have 6 minutes, and a couple of classes I saw them leaving. We will, when we come back next class, we'll do the coloring problem. Coloring problem is a fun one. It's pretty simple actually. Simple in concept, not the algorithm. Okay, then we'll after coloring we'll do the sum of subsets problem. Remember I told you, I'll just tell you what sum of subsets is, right? Let's say you have here, if I can write. Why I'm not able to write. So if I have, let's say, some numbers here, right, like 1, 3, 7, 15 and so on. Okay, what sum of subset says is, hey, if I want to come up with a value, let us say something like 25. Okay, what combinations of this subset of numbers I can use to come up with the value 25? Right, sum of subset. So if I take, for example, 15 plus 7, 22 plus 3, if I take these three numbers, it will come to 25. Maybe if I had some other numbers here like 8, 10, if I take a combination of 7, 8 and 10, I can come up with 25. So how do you, given a set of numbers, what subsets of those numbers you would use to come up with the desired target value? That is what sum of subsets problem is. We use backtracking for that. So we'll use those two, coloring and sum of subsets in the next class. Okay. Okay, I'll stop here for questions, comments, and then Chakravarti garu meer inka unnara? I don't know if Chakravarti garu is there or not. Did anyone disprove that greedy algorithm thing? Instead of me trying to solve again, if you have the answer, put it here and I'll share it with them. But I still have a few minutes if you want to hang on. Oh, what was the problem that I gave? I'll just create a new slide here, right? So I basically said you have 3 items, right? 3 items, and then one of them has what? Students, help me out here. 3 items. And I think 20. No, I don't remember it. I have to go back to that. File, recent. Okay, there it is, right? 3 items weighing 10, 20 and 30 respectively. Knapsack weighs 50. Assume the value. Okay, that's easy, right? So if I take 30, 10, 20 and 30. The second item is 100. I gave 100 here, right, already? So if I give 100 here, so for the 30 kgs value, if I give 30 kgs value, let's say I want to maximize the thing, 30 kgs values is only 10. Okay, and then kgs value is let's say the value is 30. If I say 30 or maybe 40. So if I choose 30k, greedy algorithm says choose the 30k first, then I have to choose only 20. So I'll come up with what? 10 plus 100, right? That's 110. Got it? Okay. Now, whereas that's greedy because I choose the 30k, I choose the higher weight, then I get 110 because the value is low, because I'm going by the highest weight. So 3/10, because 20 plus 3/10 is 50, right? I come to the 50 kg weight. Okay, so 20, I choose 2 times 20, that's 100 plus 100, that's 200 plus 40, so 240, right? Simple example, right? So I think you understand what I did. So greedy algorithm chooses it's always trying to maximize the weight. So I think that's where I think some confusion came. So if I take a 30 kg one, and then I chase 20, I reach, I'm happy. Because the objective there is to maximize the weight. And in the process, you maximize the value too, right? Because it's always looking for the highest number. 30 is the highest number, it chooses that. It has 10 value, and it chooses 20. It has 100 value, 120, 110. Whereas, it does not look for the lower weight one. But if I have the value there higher, 10 as 40 and 20 as 100, greedy algorithm would give me wrong solution, whereas dynamic programming would allow me to choose 20, 2 times 20 and 1 times 10. That's it. Okay. Anyone has questions? Now all this is great theory. Students, I want you to know in real life, when you have deadlines to meet, as long as your code works, the manager is happy. You always leave another day to rectify your problems, right? So, and that happens in real life, but these days kids are very sharp. They tend to do better programming than what we used to do. I do not know how many of your faculty members program still after they have become professors. They may not get time to do that. But here, when I spend countless hours in the middle of the night trying to make my code work. Okay, that's the only way we teach these classes here. Okay, I'm done with the lecture. Jntuk week, Pragati, Chaitanya, anyone has more questions, please put them in chat and I'll be happy to answer. Okay. Any questions, Andy, before I